Welcome back. In today's lecture, we will discuss conservation of mass equation. The basic principle of mass conservation states the mass of a system remains constant. This is a law that is available for a system, that is, of fixed material particles. As you know, that we like to use control volumes in fluids, so we will have to find a conversion of this law to control volumes. And for this, we use Reynolds transport theorem. We have a control volume CV and with a controlled surface. The mass can enter and cross the controlled surface. As we discussed in the last lecture, the Reynolds transport theorem says that the rate of production of the quantity, physical quantity that we are dealing with, minus the net diffusive flux out of the control volume across the control surface should equal the rate of change of physical quantity contained within the control volume, that is the local rate of change, or the rate of accumulation, plus the convective flux of the physical quantity across the control surface. When the property is mass, the rate of production of that quantity is obviously 0 if we rule out nuclear reactions. The diffusive flux in the case of mass is also 0, and the rate of change of physical quantity contained within the control volume, which is the local rate of accumulation, is del m by del t. And the last, the net convective flux of the physical quantity across the control surface is rho AV out minus rho AV in, the net efflux. This can be manipulated to give del m by del t, the rate of accumulation of mass within the control volume, is equal to the net efflux of mass across the control surface. This is the form of mass conservation equation that we use in fluid mechanics. Let us consider a steady flow in a channel where the mass is coming in at the left end and is leaving out at the right end. Clearly, in steady flow, there will be no accumulation of mass within the control volume. So, the net influx written here is 0. Rho AV in minus rho AV out is equal to 0. For constant density, when the density of the fluid does not change, the rho in is the same as rho out. So, AV in is equal to AV out. A is the area of the channel at the inlet, V is the velocity at the inlet, and similarly A out is the area of the channel at the outlet, and V out is the velocity at the outlet. The terms 1, 2 or 3-dimensional flow refers to the number of space variables required to describe the velocity profile. This conical shape represents the velocity profile in a pipe, where Vz, the velocity along the z-axis, is a function of r alone. We have discussed earlier that if the flow is laminar, this profile is parabolic. It varies like r square. We need only one variable r to describe this profile. That's why this is called a one-dimensional profile. Similarly, if we have a channel made of two parallel plates, the velocity profile Vz is a function only of y, the distance from the central axis. This is also a one-dimensional profile. If the channel is not straight but curved, but it is thin, in the sense that the cross-sectional dimensions are small compared to the dimension that we measure along the axis, then we can write the velocity along the axis is a function only of s. This again can be considered to be a one-dimensional profile. If we have a slowly tapering channel, the velocity is no longer a function of only one variable, because the velocity near the walls also changes in the y direction. So this is not truly a one-dimensional flow, but if the boundary layer where the velocity varies is thin, then the flow can be treated as a quasi one-dimensional flow. Consider a flow past a circular cylinder with a velocity v0. If we take a plane perpendicular to the axis of the cylinder and look at the flow in that plane, we would see the flow within the plane to be like this. This clearly is a function of two space variables, a vertical variable and a variable along the flow direction. This flow pattern is independent of the third dimension. That is, we could take the plane anywhere along the axis of the cylinder and we'll observe the same flow. So that's why velocity profile does not depend upon the third dimension. It's called a two-dimensional flow. In a circular pipe, and if the flow is laminar, the velocity profile is parabolic and is given as V is equal to V max into 1 minus r square by capital R square, where r is the distance measured from the axis in the radial direction and capital R is the radius of the tube. V max is the velocity at the center line of the tube where it is maximum. How is V max related to V average? To calculate V average, we need to find out what is the flow that is taking place across the whole section of the tube and divide that by the area of the tube, and that will give you the average velocity. The process is that we consider a ring of thickness dr at radius r. The velocity there is given by the formula given here, V max 1 minus r square by r square, and so we can set up integration. The volume flow rate is integral over r from 0 to capital R, Vz, the velocity at that location, which is V max into 1 minus r square by capital R square, into the area of this ring, 2 pi r dr. And this, when we integrate, comes out to be 1/2 pi r square V max after putting in the value of Vz given by the velocity profile and integrating. This is equated to V average times the area of the pipe, pi r square. And so clearly we get V max is equal to twice the V average. The average velocity is 1/2 of V max. Let's again do this problem with a turbulent velocity profile. One of the most commonly used turbulent velocity profile in a circular tube is the 1/7 power law. Vz at any radius r is V max times 1 minus r by capital R, the radius of the tube, raised to power 1/7. And we find V average in the same fashion. We take a ring of thickness dr at a radius r. We write the volume fluid Q dot as integral over 0 to r of Vz times the area of the ring, which is 2 pi r dr. And this is equated to V average times pi r square. And from this we get Q dot as 0.82 pi r square V max, and then we get V max is equal to 1.22 V average. So V max in the laminar flow is twice the V average, but in turbulent flow it is 1.22 times V average. That's because the velocity profile is much flatter than the parabolic velocity profile of laminar flows and extends very close to the walls of the tube. Let's do an example of the use of the mass conservation equation that we obtained for a control volume in this. Consider a water storage tank fed by a pipe of diameter 10 centimeter and drained by a pipe of diameter 6 centimeter. The water enters at a uniform velocity of 3 meters per second and leaves at a velocity of 2 meters per second. Calculate the rate at which the water level in the tank rises if the tank diameter is 5 meters. This is not a steady flow example. So we take an appropriate control volume. The rate of accumulation of water in that control volume is equal to the net rate of influx of water into the control volume across the control surfaces. So we have to choose a control volume that is appropriate. As far as possible, the control surface of the control volume should lie adjacent to the rigid walls across which there is no flow, like the portions here, here, and here. Why? Because they are adjacent to rigid walls, and so there is no flow across these parts of the control surface. The control surface should preferably chosen to cross the inlet and the outlet ports normal to the flow velocity to save on computational effort. Because if the surface is normal, the flow rate is simply velocity times the area of the flow. So an appropriate control volume is something like this, shown by broken lines. This portion at 1, the control surface, is perpendicular to the velocity of water. And this portion at 2 is also perpendicular to the velocity of water. So if we apply the mass balance equation, the first term is rate of accumulation of mass, which is the rate at which mass of water contained within the control volume changes. The mass of water within the control volume is rho W, the density of water, times the cross-sectional area A of the tank and the height h up to which the water is stored in the tank. This is expanded as rho W A tank into dH by dt. They plug in the value of rho W and A tank. I get 1.96 into 10 to the power 4 kilogram per meter into dH by dt. This is the rate of accumulation of water in the tank. This should be equal to the net influx of water into the tank across the control surfaces. There is an influx across one and there is an efflux across the surface marked 2. So the net efflux is the water crossing the surface at 1 minus the water crossing the surface at 2. At 1, the density into the area, 10 centimeter diameter pipe translates to 7.85 into 10 to the power minus 3 meter square into velocity, which is 3 meters per second, minus the efflux at 2, which is density times the area, 6 centimeter diameter, times the velocity, which is 2 meters per second there. So the net influx of mass is 17.89 kilogram per second. This is equated to the rate of accumulation to obtain dH by dt. We could work with alternate control volumes as well. Suppose we had chosen this control volume as shown. We are not worried about the second recommendation, which said that the control surface should preferably be normal to the velocities. At 1, the velocity is inclined at 45 degrees to this. This would complicate the calculation. The area would now increase to the area of the pipe divided by cosine 45 degrees. But when we find the flow, we will only the vertical component of velocity would contribute to flow across that area, and the vertical component of velocity would be v times cosine 45 degrees. So the product of the velocity and area would still be the same, VA. So we should get the same result. Another example of a control volume is a little bit more tricky. Here we take a control volume where the top surface is taken to coincide with the top surface of the water inside the tank. As more and more water accumulate in this tank, this part of the control surface would move. The control volume would expand. Can we apply the mass equation to this control volume? Yes, we can apply. But we must realize that while calculating the influx and efflux, we must take the velocity of the fluid relative to the control surface. Here, the control surface is moving up at the rate dH by dt. And so the average velocity of influx at that surface would be velocity of water plus dH by dt. The velocity at which the water is crossing into the control volume, the relative velocity. To state it again, the velocity of the fluid crossing the deforming part of the control surface must be measured relative to the deforming control surface. So V1 is the velocity of the falling water at location 1. The velocity of the fluid entering the control volume in a reference frame attached to this part of the control surface is V1 plus dH by dt. And if we use this equation, we would again get back the same result. Let's take another example. In very old days, the long distance train used to pick up water for their use from a ditch which was running parallel to the rails. The water was scooped up. As the train moved to the left, the water was scooped up into the reservoir. In this example, we have shown that the scoop is picking up a 4 centimeter layer of water. What is the rate of accumulation of water inside the control volume? If we choose a control volume like this, in this control volume, there is influx only at one point, only at one location, this location. If we take unit depth of the scoop, then the area of the inlet is 4 centimeter into a unit depth, 1 meter. This is the area of the scoop. And this area is normal to the velocity of water moving in. The relative velocity of water across the surface is the same as the velocity at which the train is moving forward. So if we know the velocity, we know the influx of water. The density of water times the velocity of the train times this area, 4 centimeter into 1 meter per meter depth. There is no efflux from this control surface. So rate of accumulation must be just this, the density of water times the velocity times the area of scooping. This is the control volume that we use. The speed of the train is 108 kmph. There is no exit of water. So the water is continually being accumulated inside the tank, inside the control volume. All right.